Hello, today we're going to take a look at the trigonometry exam, talk about what the correct answers to all of these problems are, and talk about some common mistakes that were made by enough students for me to call them common mistakes, and so that we can avoid making those in the future. Let's first start off with the graphs. The first one here is 3 cosine of theta plus pi over 2, and this one we need to look at for our sines and cosines where the maximum values will be and the minimum values will be. That amplitude of 3 is going to cause the maximums to be at 3, the minimums to be at -3, and then the plus pi over 2 is going to shift the entire graph pi over 2 to the left. So cosine typically has a maximum as a y-intercept and then has a 0 at pi over 2. Those points will both be moved over pi over 2 to the left, and then it will follow this pattern, and we could continue the graph, but it will look something like this. On the whole, people did a pretty good job with this question. The most common mistake was just shifting the graph to the right instead of to the left. We've got tangent of 2 theta. So let's erase this then. So tangent of 2 theta. And for this, we know that tangent has a 0 at 0 and asymptotes at all of the odd pi over 2's, and we could go through and draw all those asymptotes for our standard tangent graph. However, we have a change in b, so that is going to change the period. The period is going to be pi divided by b, which in this case is 2, so it only takes pi over 2 for our tangent graph to repeat. So that means every pi over 2, this graph is going to have a 0. Halfway between all of those zeros, there are going to be vertical asymptotes. So this is going to compress the graph of tangent. It is going to repeat more frequently than the standard tangent function does. And then tangent is always increasing. So it will look like this between all of our graphs. So the most common mistakes here were people getting the asymptotes wrong or making it more spread out instead of more compressed for the period. So we've got secant of theta plus 2. And then also we've got 2 sine of theta minus 1, so I don't have to scroll back up. So our secant graph, I like graphing based on our cosine function. So our cosine function is going to look like this based on our points that we know from the unit circle. The plus 2 is going to send it up 2. So in this case, because I'm doing this digitally, I can just shift everybody up 2. And then secant is going to have asymptotes everywhere that cosine is equal to 0. However, we're looking at this from a what is the 0 line, which in this case it's been moved up to. So everywhere that cosine is equal to 2 in this graph, secant is going to have a vertical asymptote. Then secant is going to intersect at the maximum and minimum values, and that's where the parabolas are going to be. This one people did pretty well with. Then let's look at that 2 sine of theta minus 1 over here. So we graph out, well, our normal sine graph, we know what that's going to look like. The 2 is going to change the amplitude so that our maximums will be at 2, our minimums will be at -2. Then we need to deal with that -1. So our maximum values are now just going to be at 1. Our minimum values will shift down 1 and be at -3. And any of our what were formerly zeros are going to move down 1 as well. So sine has a 0 as a y-intercept, but that's moved down 1, a maximum at pi over 2, a 0 at pi, a minimum at 3 pi over 2. So this is the pattern that the graph is going to take, and we could graph this more if we wanted, following that same pattern. Let's take a look at the graphs from the other version of the test. We'll just do all of the graphs together, then all of the equations together, then all of the inverse trig functions together. So secant of theta plus 1. We're going to take just the normal secant like we did here, and it would just be up 1 instead of up 2. So it would look like this. Okay, well, these parabolas did not shift when I shifted everything else, but the maximums for these parabolas would be on the x-axis. Our next graph is cotangent of 1/2 theta. So we've got, let's do a new graph. Just like with the tangent, the biggest issues that people had were putting the asymptotes and zeros in the wrong spot, mixing up the ones for tangent and cotangent, and then not appropriately implementing the period change. So the period here is going to be pi divided by b. B is 1/2, so the period is going to be 2 pi. We need to figure out what the y-intercept is going to be, and for cotangent, that y-intercept is going to be a vertical asymptote. Since the period is 2 pi, every 2 pi, this cotangent function will have a vertical asymptote. Halfway between the asymptotes, so at pi and -pi here, cotangent is going to have a 0. Cotangent decreases over its entire domain, so sketching the graph, it will look something like this. Our other two graphs, the sine of theta plus pi, and then, was it 2 cosine of theta minus 2. So the sine of theta plus pi, we just take our standard sine function, and then we are going to shift it left pi. So what you can do is look at all the points individually and just shift them to the left pi, or once you get the pattern of what's happening, once you shift a few, so this will go left pi, or sorry, the 0 will go left pi, the maximum will go left pi, the 0 will go left pi, the minimum will go left pi. You have this new pattern of what's going on and can sketch the graph of the function. The 2 cosine of theta minus 2 is going to look very similar to how we did this 2 sine of theta minus 1, where the maximums would be at 2 and -2, but then you move down 2, so the minimums are at -4, the maximums are at 0, and the x-coordinates do not change at all, so it would look something like that. All right, just a quick sketch for time purposes. Now let's take a look at some of the equations. Each version had one problem where everything is already in terms of one trig function, and we just need to either use u substitution or just factor as is. So this one, I'll use u substitution, and then we won't for the other one. So u is cotangent of x, so we've got u squared equals negative 2u minus 1. We'll add 2u and add 1 to both sides because this is quadratic, so we want it set equal to 0. We've got u squared plus 2u plus 1 is equal to 0. We go through and factor that to u plus 1, the quantity squared. We can square root both sides, so we have u plus 1 is equal to 0. Subtract 1 from both sides, and now once you have u by itself, you can substitute the cotangent of x back in. So then we take the inverse cotangent of both sides. So where is cotangent equal to negative 1? And that's going to be at 3 pi over 4. On the other version, the one where everything was already in terms of one trig function, was also number 5. So in this case, it's all in terms of secant squared theta. So let's subtract 2 secant squared theta from both sides, subtract 3 secant of theta from both sides, and then see what happens because it's quadratic. So when we subtract that from both sides, we'll just have not sine, secant squared theta minus 3 secant theta plus 2 is equal to 0. We can factor this to secant of theta minus 2, secant of theta minus 1. We'll set each of those equal to 0. So we're looking at secant of theta is equal to 2, and then secant of theta is equal to 1. So secant of theta is equal to 2, where cosine of theta is equal to 1/2, which is going to be at pi over 3. And then secant of theta is equal to 1 at theta equals 0. The most common mistakes with this type of problem were just some little algebra errors with either factoring or combining like terms, but on the whole, these were pretty good. Each of the versions also had a problem where you could use a Pythagorean identity, like number 6 here. We know that tangent squared theta, or x, plus 1 is equal to secant squared x. And I know that there were some issues with this one, with this specific problem, with people not knowing what to do with that plus 1. We can manipulate the identities. If you subtract 1 from both sides, you know that tangent squared x is secant squared x minus 1. And then we can take this secant squared x minus 1, substitute it in for your tangent squared, well, theta, and then the entire problem is in terms of secant. So we've got secant squared theta minus 1 is equal to secant of theta plus 1. Just watch your algebra here. So we've got secant squared theta minus secant of theta minus 2 is equal to 0. Then we can factor, and once you have it in terms of one trig function, you can either use u substitution or not. It's up to you. So we've got secant of theta minus 2 times secant of theta plus 1 is equal to 0. So we set each of these equal to 0. And that is still at pi over 3 like we saw on the last problem. So we've got secant of theta plus 1 is equal to 0. Secant of theta is equal to negative 1. When we take the secant inverse of both sides, we get theta equal to pi. Now let's take a look at that problem on the other version. And that is going to be number 9, where we have sine squared x is equal to 3 cosine squared x. This one I'd want to do in terms of cosine because then we don't need to deal with distributing the 3. You could distribute the 3 if you would like. We know that sine squared x plus cosine squared x is equal to 1. So we can subtract 1 from either side, or subtract either the cosine squared x or the sine squared x, and end up with one of them isolated. So in this case, 1 minus cosine squared x is equal to sine squared x. We can add cosine squared x to both sides. So we end up with 1 is equal to 4 cosine squared x. Divide both sides by 4. When we take the square root, don't forget you have to look at the positive and negative sides. So we know that cosine of x is equal to 1/2, and cosine of x is equal to negative 1/2. So x is either equal to pi over 3 or 2 pi over 3. So some common errors with these were really specific to each one, of either having some issues with the secant values or not remembering that you also need to look at when cosine of x is equal to negative 1/2. Each version also had one of the 4 was one where you had to factor out a common factor. So that's number 8 on this version, where each of these terms is going to have a tangent squared x. One thing that tells me that we're going to need to look for a common factor here is the fact that tangent and sine are not in a Pythagorean identity together. You don't want to divide both sides by tangent squared x, because then you might miss out on solutions. So what we'll do is just factor it out. So we have tangent squared x multiplied by 2 sine of x minus 1 is equal to 0. You can always check your factoring by distributing again, and if you distribute and get the same thing, you have factored correctly. We set each of these equal to 0. For the tangent, we'll take the square root of both sides. Tangent of x is equal to 0 when x equals 0. And then we'll add 1. We'll divide by 2. And sine of x is equal to 1/2 when x is equal to pi over 6. Let's take a look at our one with factoring a common factor out on this version, also number 8. So we'll start out, since we've got sine of x and cosine of x multiplied by one another, let's start out by getting this expression equal to 0. So we've got subtracting cosine of x from both sides, not dividing, again, because that will miss out on some solutions. So we've got 0 is equal to 2 sine x cosine x minus cosine of x. We can factor that cosine of x out. Set each equal to 0. And this 2 sine x minus 1 is the same expression or equation that we had before, like that we just did. So it's x equals pi over 6. Cosine of x is equal to 0 when x is equal to pi over 2. So with those problems, it was really just if you divided both sides by that common factor, you'd miss out on solutions instead of having those. Or in here, either somehow dividing by cosine of x and ending up with a 0 instead of a 1. Let's look at the last equation for these two different versions. So the last one, like number 9 here, is one where we are going to need to square both sides before using a Pythagorean identity. Please do not try and just go, all right, well, we'll square this, and distribute the squared. You cannot distribute the squared. That is not how that works. So what you want to do is let's add cosine of theta to both sides. Then you're allowed to square both sides. So our left side will be sine squared theta. The right side will be cosine squared theta plus 2 cosine theta plus 1. Now we can take that sine squared theta and substitute in 1 minus cosine squared theta. Everything's in terms of cosine. If you would like to use substitution, you can. We can subtract 1 from both sides. We can add u squared to both sides. So we have 0 is equal to 2u squared plus 2u. We can just factor out a 2u. We're left with u plus 1. Set each equal to 0. So u is equal to 0, or is u is equal to negative 1. We substitute our cosine back in. So we end up with pi over 2 or pi. If you end up substituting 1 minus sine squared theta in for cosine of theta, like for example, if you had instead moved sine to the other side, you would still end up with the same answers. Let's look at this on the other version. So here, this one, people made a few more mistakes, and it was not with any of the pre-calculus part, it was with some algebra. So the first thing we want to do is subtract 2 sine theta from both sides. So we end up with root 3 cosine theta is equal to negative 3 sine theta. Now we need to square both sides. When you square both sides, you have to square everything on the side. Not a lot of mistakes with this side, but I saw enough people not make that a positive 9, whether it was still a negative 3 or it was a positive 3 or it was a negative 9. Negative 3 squared, it's squaring, it's negative 3 multiplied by negative 3, which will give us a positive 9. Then we'll divide both sides by 3. And in this case, I mean, you can use either one, but I would substitute in 1 minus sine squared theta for the cosine squared theta, just because then you don't have to deal with distributing the 3, which is something else that I saw a few people make a mistake with. Add sine squared theta to both sides. Divide by 4. And this, you will get slightly different answers if you use sine or cosine, but it's okay. They were both marked correct as long as your steps were correct. So we're looking for when sine of theta is equal to a positive 1/2, and also sine of theta is equal to negative 1/2. So we've got pi over 6 and negative pi over 6. That is all the equations. Let's just quickly go through our inverse trig to finish this video out. So with this one, it was the same 10a on both versions. We start on the inside out. So cosine of pi over 2 is 0. So now we have an expression that is tangent of sine inverse of 0. Sine inverse of 0 is 0. So then tangent of 0 is 0. Cotangent of negative pi over 3 is going to be a pi over 6, but cotangent, we use 5 pi over 6 in that second quadrant. Cosine inverse of 0 is pi over 2. Secant inverse of negative 1 is pi. Secant inverse of negative 2 root 3 over 3 is going to be 5 pi over 6 as well, because that's the same location that same angle as cosine inverse of negative square root of 3 over 2, because we're looking at the reciprocal function and the reciprocal value. On this version, 10a is the same. You end up with 0. Tangent inverse of negative square root of 3 is negative pi over 3. Cosine inverse of root 2 over 2 is pi over 4. Cotangent inverse of negative 1 is going to be 3 pi over 4. We know that it's going to be a pi over 4, but cotangent, we use 0 to pi. So any negative values will have an angle in the second quadrant. And then cosecant inverse of 2 root 3 over 3. Same idea as what we were looking at with 10e over here. So it's going to be where sine is equal to square root of 3 over 2. So we know that this is going to be pi over 3. And then 7 was you just trying to reflect on these values, see what you've been having trouble with, try and think about some of those strategies that work for you. If you have any questions with this, please let me know, and thank you for watching.